Alright, so today what we're going to be looking at is how do we end up being able to figure out horizontal asymptotes and the like, or end behavior in general, when we are dealing with functions that, well, maybe it's not really obvious how we can figure out their end behavior with the usual methods that we've seen before. So here is an example of the sort of thing that I mean. What if I am trying to sketch something like e to the x divided by x? How do I know what happens as x approaches plus or minus infinity? Now, we've talked, of course, about limits at infinity before, right? And so when we dealt with things like rational functions, we know how to deal with these kinds of things. We know how to look at the end behavior for rational functions. But in this case, it is not really obvious what to do here. And more generally, there are other types of problems that we could ask as well, where maybe we are dealing with the limit as x approaches a of, let's say, f of x divided by g of x, where, let's say, the limit as x approaches a of f of x equals the limit as x approaches a of g of x equals 0. Or maybe it's one where they are both diverging to infinity. In other words, maybe we've got a limit where both of the f and g are both divergent. And let me see if I can find a slightly better pen. I've been having the worst luck with pens today. Even worse than usual. I always have bad luck with pens, but this has been particularly egregious today. Okay, so the question is, what do we do in these kinds of situations? Well, you'll notice that actually this sort of situation is one of those where both of these things are going to infinity, right? And so that is sort of wherein the problem lies. Actually, in this case, as x goes towards negative infinity, we're okay, because the numerator would be going to 0 and the denominator is blowing up. So overall, this thing is going to 0. But as you go towards positive infinity, that's where you get a problem, because now both the numerator and the denominator are going towards infinity. So what can we do in these kinds of situations? Well, the answer is something called L'Hopital's rule. And there's a couple of different ways of spelling this. So it's either spelled like hospital, or it is spelled with an O with a little caret over it. And I don't actually know what that is called, but it is a symbol for use in French. And yeah, so you can use that in these types of situations. Now, what is L'Hopital's rule and what do we do with it? Well, L'Hopital's rule is something that we can use whenever we're trying to find one of these limits and we already know how to take the derivatives. Now, I'm going to return to that in a moment because there's something that people, I think, sometimes overlook when talking about L'Hopital's rule, and it is really, really important that we be careful about when it is permissible to use L'Hopital's rule and when it is not permissible to use L'Hopital's rule. L'Hopital's rule is essentially applicable to any situation in which what we have is a limit in indeterminate form. So what is an indeterminate form of a limit? Well, it is something where we have the limit as x approaches a, including possibly plus or minus infinity, of f of x over g of x, where f and g are both approaching 0, or f and g are both approaching plus or minus infinity. Or, finally, we could have this situation, the limit as x approaches a, f of x times g of x, where f is approaching plus or minus infinity and g is approaching 0. Now, any of these are considered indeterminate form, and L'Hopital's rule applies in these situations. We're only going to prove it in one of the situations, but proving it in general is pretty similar. So, there's like a bunch of special cases that you have to deal with, but they all go pretty much the same. So what can we do in these kinds of situations? What would we be able to figure out? Well, I'm going to deal with the ratio where both of them are going to 0, because that's the one that I think is the most straightforward to do, and then we'll sort of say a few things about why all of the others follow in a fairly similar manner. So let's suppose that we are looking at the limit as x approaches a of f of x divided by g of x, where f and g are both approaching 0 as x approaches a. Well, here's what we can do in this situation. Supposing here that f and g are differentiable at a. So differentiable at a. Now, of course, this also means that they are continuous at a, and therefore that f of a and g of a are going to be equal to 0. In that case, what we can do is we can replace this with the limit as x approaches a. So we have f of x over g of x. This would be equal to the limit as x approaches a of f of x minus f of a divided by x minus a times x minus a divided by g of x minus g of a. Now, I can do this because, well, I'm just multiplying on the top and the bottom by x minus a, which I can certainly do because the limit doesn't care about what happens. Hey, thanks. The limit does not care about what happens at x equals a. So what can we say about this quantity here? Well, actually, this quantity is pretty simple to see. This is really the limit as x is approaching a, f prime of x divided by g prime of x. In other words, we've just replaced our functions, f and g, with their derivatives, f prime and g prime. And that's it. And that's really all that L'Hopital's rule says. It says that if you have an indeterminate form, then you can replace your f and your g with their derivatives, and you can still compute the limit. Now, like I said, this is only one of several of the cases where we're dealing with indeterminate forms. So, for instance, if we're talking about limits at infinity as opposed to limits at a finite number, well, then things become a bit trickier because you can't really talk about f evaluated at infinity and things like that. So the proof involved, it gets a little bit more involved and things like that. But as I said, all of the different proofs, they go fairly similarly. I'm not going to bother showing you all of the details there. we will stick with just this one. Now, it's very important that when you use L'Hopital's rule, that you first check to make sure that you really do have an indeterminate form to work with. Because if you're not dealing with an indeterminate form, then you can't just automatically replace functions by their derivatives in general. If it's not an indeterminate form, then that is not a valid thing to do. The other thing that I want to observe is you got to be careful what you use L'Hopital's rule for. For instance, suppose that I wanted to find the limit as x approaches 0 of sine x divided by x. This is indeed in indeterminate form. However, although I would like to be able to use L'Hopital's rule for this, and we could, now that we know the derivative of sine of x, the problem is that we needed to compute this limit in order to find the derivative of sine of x. And you can't use L'Hopital's rule unless you already know the derivative. So, to compute this limit, you can't technically use L'Hopital's rule because L'Hopital's rule requires that you already know the derivative, and we're trying to find the derivative by computing this limit, and so it would be a circular argument if we were to try to use L'Hopital's rule to compute a limit like this. So this is where I'm saying you got to be really careful about what you do with L'Hopital's rule versus not with L'Hopital's rule. So let's take a look here at some examples of applying L'Hopital's rule to some specific instances. First of all, let's go back to this question of the limit as x goes to infinity of e to the x divided by x. Now, this really is in indeterminate form. In fact, this is what we call infinity over infinity form. So the different indeterminate forms, there's infinity over infinity, 0 over 0, and 0 times infinity. Infinity over infinity means that the numerator and the denominator are both blowing up to infinity. So what we can do is we can replace this with the limit as x approaches infinity of e to the x divided by 1. Well, this is going to blow up to infinity because, of course, as x goes to infinity, e to the x goes to infinity. And as x goes to infinity, 1 remains as 1. So this is going to blow up to positive infinity. What if we had the limit as x approaches infinity of x squared divided by e to the x? Well, this would also be an infinity over infinity form. And I can replace this with the limit as x goes to infinity of 2x divided by e to the x. Now, this is itself, once again, an indeterminate form of infinity over infinity. And I can replace it, therefore, with the limit as x goes to infinity of 2 over e to the x. Now, the denominator is blowing up to infinity and the numerator is remaining constant, so this is going to be equal to 0. Now, there's an interesting observation that we could actually make, sort of generalizing these points that we've seen in these two examples. So, let me show you the following interesting observation. The limit as x approaches infinity of e to the x divided by p of x, where p is any polynomial, this is always going to be equal to infinity, and the limit as x approaches infinity of p of x divided by e to the x, this is always going to be equal to 0. Why is this? Well, the reason is because when we apply L'Hopital's rule, we're going to decrease the degree of the polynomial at each step. And after a finite number of steps, it's going to come down to a constant. But the e to the x is going to remain unchanged. So therefore, eventually, we're going to have e to the x over a constant in this first case, or a constant over e to the x. And so we get infinity or 0. Now, an interesting thing about this is it means, in some sense, we can say e to the x grows towards infinity faster than any polynomial does. In other words, if you take this ratio of e to the x divided by a polynomial, it blows up towards infinity no matter how big your polynomial is. And this fact is very important in computer science and in studying algorithms, because one of the important things about algorithms is we like to look at these algorithms and figure out how efficiently we can accomplish some kind of a calculation. In other words, how many steps does our algorithm take? Well, generally speaking, the number of steps depends upon the complexity. And if we're dealing with something that takes a polynomial number of steps based on the complexity, that is considered really, really good. Because if it only takes a polynomial number of steps, then the number of steps does not grow that quickly with the complexity. Whereas if it grows like the exponential of the number of steps, well, that means that the number of steps, if the number of steps grows like the exponential of the complexity, then that means that the number of steps is going to grow really, 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 really quickly, okay? So we like things in computer sciences and in the study of algorithms, we like to have a situation where the number of steps grows like a polynomial. Hopefully. I mean, that's, we hope that that's what we get. Doesn't always work out that way, but that is sort of ideal if you can get it that way. Let's take a look at some other examples of using this kind of thing. So let's suppose that we want to look at the limit as x approaches 0 of e to the x minus 1 divided by sine x. This is going to have 0 over 0 form. Now, what I'd like you to do is pause this for a moment and take a minute and see if you can figure out what this comes out to be. All right, we're able to figure anything out. So if we use L'Hopital's rule here, this is going to become the limit as x approaches 0 of the derivative of the numerator here is just e to the x. And in the denominator, we are going to have cosine x. Now, this is no longer an indeterminate form. This we can actually find by just plugging in x equals 0. So this is going to become e to the 0 over cosine 0, which is 1 over 1, which is equal to 1. So there we go. We have ended up figuring out what this limit is going to be. Now, what do you do if you have something which is in the 0 times infinity form? Well, if you have something in the 0 times infinity form, then you want to rewrite it as a ratio, because in order to apply L'Hopital's rule, you really have to have a ratio. In other words, you have f over g or something like that. But fortunately, that's not really that big a deal, okay? Because the thing is that you can always kind of rewrite things that way if you want to. So let's suppose that we want to look at the limit as x approaches 0 of tangent x times let's say 1 over x. So this is going to, and let's do just from the right, just to make things a bit easier for us here. This is going to be of the 0 times infinity form. But what I can do is I can think of this really as the limit as x approaches 0 from the right of tangent x divided by x. And then I can take the derivative on the top and the bottom. So this is going to become the limit as x approaches 0 of secant squared x divided by 1. Now, secant is, of course, 1 over cosine, and therefore this is going to become 1 squared over 1, which is going to be equal to 1. So there we go. We've been able to figure this out. Now, this is maybe sort of a artificial kind of thing because like 1 over x is, of course, dividing by x. But I just wanted to give an illustration here of what you do when you are dealing with 0 times infinity forms and the like. Give me a second here. Okay, so here's another example that maybe is a little less contrived with a 0 times infinity situation. So what if we were dealing with the limit as x approaches 0 from the right of x times the natural log of x? Well, in this case, the way that I'm going to think of this is I'm going to think of this as the limit as x approaches 0 from the right log x over 1 over x. And, well, obviously this is an indeterminate form. These are both blowing up to infinity. Technically, log is going to negative infinity, but, we are indeed in infinity over infinity form. And if I take the derivatives here and use L'Hopital's rule, we're going to have limit as x approaches 0 from the right, 1 over x divided by negative 1 over x squared. And so this is going to become the limit as x approaches 0 from the right, 1 over x times minus x squared, which is going to be 0. Because, of course, we can now cancel the x with one of the x squareds here, and we end up with 0. So, in this case, we have sort of an example where we started with a 0 times infinity form, and then we were able to rewrite it this way and use L'Hopital's rule in order to figure out our limit. Let me give you a couple of examples to think about. Actually, here's one that I would like you to take a minute to try yourselves and see what you are able to get. So, see if you can find the limit as x approaches 0 of sine of 4x divided by sine of 7x. So, pause the video for a minute, see what you can figure out with this, and then we'll come back to this. Okay, so we're able to get this. You'll notice that this is a 0 over 0 form. And if we apply L'Hopital's rule, this becomes the limit as x approaches 0 of 4 cosine 4x divided by 7 cosine 7x. And now, if I plug in x equals 0, well, this just becomes 1 over 1. So this is 4 over 7. And there we go. We're done. Let me give you another example to think about here. So what about the limit as x approaches 0 of, let's say, sine of 3x divided by e to the 2x minus 1. So once again, pause this, take a minute, and see what you can do with it. Okay, so this is going to be a 0 over 0 form again. And if we apply L'Hopital's rule, we will have the limit as x approaches 0, 3 cosine 3x divided by 2 e to the 2x. And if I now plug in x equals 0, well, this is going to be 1, this is going to be 1, and so we end up with 3 halves. So there we go. We've been able to figure this out. Now, you might wonder, how does this tie into the stuff that we've been talking about in terms of sketching graphs and whatnot? Well, the answer is that in order to sketch graphs, we often need to be able to talk about limits, including limits at infinity, but also possibly limits where we're simply asking, some quantity, some fraction may or may not be defined at a given point, but we still need to be able to talk about the limit there. Well, that is what L'Hopital's rule allows us to do now. So we can now use L'Hopital's rule to figure things out, like the end behavior of functions that otherwise we wouldn't be able to figure out. Now, there's one more sort of indeterminate form that we need to consider. And this happens when we're dealing with indeterminate forms that involve powers. So let me write down the sorts of forms that I'm talking about. Maybe we have something like 1 to the infinity, or we might have something like 0 to the 0, or we might have something like infinity to the 0. In other words, we have a limit that involves two functions, and one function is in the exponent of the other function, and the resulting limit is not in a determinate form. So how do we deal with these types of situations? Well, we cannot just deal with them directly by using L'Hopital's rule, but here's what we can do. It's easiest, I think, to illustrate this by just showing you an example here, so that's what we're going to do. Let's suppose that I want to deal with the limit as x approaches 0, or actually, let's do the limit as x approaches infinity of x to the 1 over x. Now, the thing that you'll notice here is that this is in the form infinity to the 0, because x is, of course, approaching infinity, and 1 over x is going to be approaching 0. Now, here's what we're going to do. Let's let y equal x to the 1 over x. Then what we can do is we can say the natural log of y is 1 over x times the natural log of x. And so what we can then look at is the limit as x approaches infinity of y, or of log y, is the limit as x approaches infinity of log x divided by x. And this is going to be equal to the limit as x approaches infinity of 1 over x divided by 1, which is equal to 0. So you'll notice here that what we've actually done is we've computed the limit of the log. Now, the reason why this works is because the exponential function is continuous. And therefore, what we can say is that the limit as x approaches infinity of y is equal to e to the limit as x approaches infinity of the log of y, which in this case is e to the 0, which is equal to 1. Now, I just showed you how to do that in this one particular instance, but in general, this is what you're going to do in any of the other situations where you have one of these types of indeterminate forms, okay? So what you're going to do is you're just going to take the natural log. This will give you one of our indeterminate forms where we can use L'Hopital's rule. And then you're going to use L'Hopital's rule, calculate the limit, and then you take the exponential of that limit and it gives you your original limit back. So it's actually not too bad to deal with. It's just a matter of using logs and limits like this. All right, so what we're going to do next time is we will just kind of summarize all of the different things that we can say about curve sketching. And I'm going to encourage you to take a look at some various examples of curve sketching and kind of practice along with those examples, doing your own curve sketching in the process. So that's what we'll be doing next time, and I'll see you in a couple of days.